out, first of all, there are only three magnetic elements: iron, cobalt, and nickel. Iron, cobalt, and nickel are the only magnetic elements. And before we dive too much further into basically how magnets work, I want to know some background information. What kind of explanation of magnets could a second grader give me? What kinds of things about magnets would a second grader know? Opposites attract. So magnets, we've got opposites attract. What else would a second grader be able to tell me? That's not entirely accurate. No, she probably was misinformed. Okay, they can wipe data off of hard drives. Probably parents when you start bringing your magnets over to your computer and trying to place them on it. All right, anything else? How about like poles repel? Like poles repel? No, though that's literally the opposite of that. Okay, and I'll put on here that magnets can erase hard drives. That's fine, but don't get distracted by them. And distracted. All right. So beyond this, we want to have a little bit more understanding for what actually drives magnets. To dive into that, though, I want you to go ahead and take your toys out of the box. And you're going to place one neatly on your notes or on a piece of paper. Okay? The other toy you should have is a compass. Okay? So first of all, hold your compass up and far away from literally anything else, especially magnets. And one of the two needles is going to point that way-ish. Mine's kind of off to the side a little bit. And one of them is going to point that way. The needle, oh wow, okay, that's weird. This hand is making the compass spin. So the needle that points that direction towards the board is the end pole of your compass. The needle that points that way towards the clock is the S pole of your compass. Some of them may have the red one pointing up here, some of them may have the white one pointing up here. It doesn't really matter which is pointing to the north, because the way they get stored in this classroom is nearby a whole bunch of magnets. And as you'll learn later, we can change the magnetic orientation of these things. And that may happen to some of them. So just be aware that you may not have the same orientation magnet as your neighbor. So mine, the white arrow points, white arrow? Yeah, the white arrow is pointing towards the north, so it is the end pole magnet. And what I'm going to do is I'm just going to set it down next to my larger magnet, and I'm going to use it to find the direction that the magnetic field is pointing at different points. And I'm just going to lift up the compass and draw an arrow in the direction of the end pole of my compass at various different locations. I'm going to do this, I don't know, several times. So go ahead, take a moment, draw some arrows indicating the direction that the compass points when it's around your magnet at various locations. Drawn at this point. where have you seen something similar to this? Right, the electric fields. So what we've just done is we've mapped the magnetic field. Just like gravity, electricity, magnetism is also a field force. So magnetism is a field force. And just like electric field, we have a few different rules for actually drawing out an electric field. So first of all, I'm going to play a little bit of connect the arrows with these and map out some electric fields. Let's go out and around in there. Let's go out like this, around and like that. Okay, just kind of showing generic directions that these magnetic field lines would follow. So first of all, when we drew electric field lines, what were some of the rules for drawing electric field lines? Okay, so the number of lines had to be proportional to the charge of the electric charge, whether it was protons or electrons. Okay, we could either do that by how many arrows there were, or how long the arrows were, or the opacity. There were a few different options. But in one way or another, the lines had to be proportional to the electric charge. Here, number of lines or strength of lines, opacity of lines, is somehow proportional to the magnetic field strength. So lines are proportional to magnetic field strength. What else did we have for electric field lines? There were two other rules. What were they? They couldn't cross. Conveniently, magnetic field lines can't cross. Cannot cross. And lastly, okay, so for electric field lines, they started at positive charges or infinity and ended at negative charges or infinity. For magnets, it's almost identical. It's just that there is no infinity option. They start at N poles and end at S poles. Better? Magnetic field lines start at N poles and end at S poles. Okay. One of the big ramifications of this is that there are no singular poles for magnetism. They always come in pairs. For electricity, we can have an electric monopole. It's called a proton or an electron. For magnetism, they simply don't exist. And part of the reason for that is magnetism is more like a direction than a charge. So magnetic monopoles meaning simply an N pole or an S pole. Magnets that are just N or S do not exist. Okay, so when we're thinking about magnetism more as a direction and less of as like a charge, one of the things that I want to point out is that it's a continuous direction. So if I take my drawing from up above and I just continue these lines through my magnet, we find that we actually create magnetic loops that go inside the magnet from S to N and then outside from N to S, making a continuous loop. Okay? This is because magnetism is caused by motion. On some fundamental level, in all situations, magnetism has to do with the motion of electric charge. Now, what that motion is exactly, it can vary. We'll talk a lot next week about electromagnetism and how you build an electromagnet, and then we'll build an electromagnet. But in terms of making a permanent magnet, it relies on what we call domain theory. Domain theory. Okay? The concept behind domain theory is that a magnet is made of a bunch of mini magnets. So if I take my magnetic bar and I break it into a whole bunch of groups of atoms, tens of thousands of atoms, grouping maybe a centimeter in diameter, each of these groups of atoms is called a domain. A group of atoms is called a domain. Within that domain, all of the electrons have spin. I just put giant air quotes around that if you didn't see, so they all have spin. Now, the reason I'm doing that is because when we originally started understanding magnetism, we believed that the electrons were, in fact, spinning in a specific direction, and the direction that they were spinning caused a magnetic field. We've come to find out that, yeah, no, that's not how it works. But we stuck with the term spin because we had nothing better, so we just ran with it. Okay? So in that domain, all the electrons have the same magnetic spin. All electrons have the same magnetic spin. Which, running with the concept of direction, the whole spinning thing was really nice because if you're spinning in one direction, you're going to generate an N pole in one direction. And where's the S pole? Well, it's simply the opposite direction. And the idea of this motion is really convenient. So when we get all these domains having their own magnetic spin, we create a permanent magnet if all those domains share each other's magnetic spin. So if this one has a spin that way, and this one has a spin this way, and this one has a spin that way, they cancel each other out. And we wind up with an object that is not magnetic. So not magnetic. However, if each of these domains shares its spin with the other domains around it, then we wind up with a permanent magnet. So they're all, in this case, pointing in this direction. Magnet. Okay. Questions there? Is that we're going to talk about for creating a permanent magnet. The first one you just saw, violent vibrations in the presence of a magnetic field. Violent vibrations in a magnetic field. All right, somebody got another way to give an object kinetic energy other than just smacking it around. No. However, when you give it love and attention, what's it going to have for a feeling? Come on, run with your analogy here. Nothing? What? It's going to have a warm, fuzzy feeling, right? Okay. Heat. Okay, so the next option is to heat it up. So extreme heating in the presence of a magnetic field. Heating in a magnetic field. Again, giving it enough kinetic energy that the domains can shift. Lastly, just leave one in a magnetic field for enough time, and it's just gonna kind of happen. So long durations of time. Long durations of time. In a magnetic field. So the first permanent magnets in human history were what we called lodestones, largely found by the Chinese. They were basically rocks with some iron ore in them that they found to have magnetic properties. They had turned into magnets simply because they sat in Earth's magnetic field for long enough in a specific direction or orientation, that they gained magnetic fields. If you go to lava flows, where you find that the rock has cooled, compasses don't work there so well because they just kind of want to point at the ground because the ground is a giant magnet because of all the iron ore in the the lava rock. Looking at this list of things, what do you notice as a trend? They all need to be in the presence of a magnetic field, which begs what question? Where does that field come from? The Earth. Okay? You looked like you had another answer there. So, Earth's magnetic field. That's our whole next section here. So, geomagnetism. All right? So, I'm going to go ahead and draw our Earth here. By our Earth, I totally mean a donut. And you got to put the frosting layer around the donut. Okay. Somebody explain my drawing to me before I decide that I need donuts, right? Yeah. Got the Earth's core and the Earth's crust. And in between, a mantle. And if I wanted to be really specific, I could talk inner core, outer core, upper mantle, lower mantle, lithosphere. Yeah, let's not. Okay. So what part of this drawing actually causes Earth's magnetic field? So the core is usually the go-to answer. And people usually think, oh, it's the core. It's made out of iron. That makes sense. We just said iron was a magnetic metal. So the core is a giant magnet. But then we run into the same problem again. If the core is just a giant magnet, where did its magnetic field come from? But sure, heat, but what magnetic field in that extreme heat? So we still have the same problem, which fortunately we don't actually have this problem because the core is not the primary concern here. The outer core and the mantle are actually what we are interested in. In that area, we have convection cells. Throughout the mantle and the upper part of the core, we have magma that is convecting through this entire section. So everybody knows hot stuff rises, cold stuff falls. But what's significant about this hot stuff rising is that it's ionized, meaning that the magma and such that is being convected has lost its electrons. So we're moving large amounts of charge up and down throughout the mantle of the Earth. And as we mentioned earlier, somewhere up there, I don't remember where I wrote it, the motion of charge can cause magnetism. And fundamentally, that's where all magnetism is coming from. Earth is a giant electromagnet. Earth is an electromagnet. And in fact, it has less in common with the magnets that you guys are holding in your hands than it does with that one that I can turn on and off that dropped the tin can earlier this year. That actually has more in common with Earth than your permanent magnet does. Okay? So Earth is an electromagnet. We've got convecting or convection of hot materials moves charge. All right, so now we've got a source for that original magnetic field that we can create all these others in. That's cool. But we actually care about geomagnetism for more reasons. Why do we care that Earth has a magnetic field? Navigation, that's cool. That's kind of sweet. Being able to say that way's north, that way's south with a compass and not needing to navigate by stars. Why else would we care that Earth has a magnetic field? Any ideas? What about them? They're important. Yes. Again, navigation. So why do we care that Earth has a magnetic field? Bingo! So the sun doesn't destroy us. Earth's magnetic field protects us from cosmic rays all the time. Without Earth's magnetic field, the sun's rays would rip away our atmosphere and torch the surface of the Earth. So, magnetic field protects from cosmic rays. Specifically, we're talking gamma and X-ray radiation. Gamma and X-ray radiation would not have allowed Earth to have any life on it if the magnetic field hadn't been there to prevent it from reaching us. We can also actually look at other planets in terms of whether or not they have life or have the potential to have life based on whether or not they have a magnetic field. First of all of the gas giants have a magnetic field. If we were able to see magnetic fields, Jupiter's magnetic field would be the second largest object in the sky right behind the sun. So we would very easily see Jupiter in a lot of the sky. As it is, Jupiter's magnetic field wreaks havoc with your radio at night. If Jupiter is out and you drive in an area away from cities, and you tune your FM radio to the right frequencies, you will actually hear Jupiter's magnetic field over your radio. It sounds just kind of like random noises, but it's not the same as other frequencies would be producing. Okay. Beyond that, we can look at Mercury. Mercury does not have a magnetic field because it's a piece of rock. There's nothing really left there. It's boring. Venus has some magnetic field, but most of Venus's atmosphere sticks around because Venus has a lot of atmosphere, and there's so much pressure there, it's ridiculous. But the best example to talk about magnetic field are Earth and Mars. If we roll back 4 billion years to just after the period of heavy bombardment, actually it's closer to 2 billion years, so where we've got a stable couple of planets, we find that Earth and Mars were very, very similar. You've heard that before, I imagine. Both had the potential to have life start. We believe that there was liquid water on Mars at some point, possibly with something living in it. We don't know. That's one of the cool questions. But why Mars doesn't currently have that option is because Mars is smaller. Because Mars is smaller, think about a couple of maybe large objects that you throw into a fire. You throw a larger log into a fire, you throw a smaller log into a fire. You let the fire burn out. Which one's going to be hot for longer? The larger one. The larger object has more insulation, so it stays hotter for longer. The smaller one cools much faster. Okay, so because Mars cooled faster, its convection has slowed down. With less convection, it doesn't have as much of a magnetic field. With less magnetic field, Mars's atmosphere has begun to be stripped away, and it's not left with nearly as much as it originally would have had. Earth, fortunately, is bigger, therefore has more insulation, keeps its heat for longer, keeps its convection for longer, keeps its magnetic field for longer, keeps its atmosphere for longer. It's kind of a chain of things all based on size. So when we look for planets outside of our solar system that could potentially support life, we look for bigger ones because bigger ones would be warmer ones, would be having more magnetic field, would have an atmosphere. All right. Questions about any of that train along geomagnetism? Okay, next piece. North, south. How many of you have caught on to the fact that I keep saying N pole and S pole, not North Pole and South Pole? Okay, there is a reason. And that reason is, well, pick up your compass. Which pole is pointing that way? The N pole, right? Okay. Why is the N pole pointing that way? I mean, that way-ish. Why is the N pole pointing that way? Quick, go hire your inner second grader. Okay. Opposites attract. Okay. So if this is an N pole pointing that way, what's got to be up there? An S pole. So while it's geographic north has a magnetic S pole. That is why your magnetic N pole points towards it. So S pole, N pole. So I use the words north and south specifically to talk about geography, and I use N and S specifically to talk about magnetic poles. Because if I start talking about the North Pole for both of them, yeah, we're going to get confused real quick because those two are not the same kind of pole. Does that make sense? Say again. So we're in South Magnetic Dakota? Yes, we are in South Magnetic Dakota. All right. We have to rename it that. A couple other things about magnetic versus geographic poles. They're not at the same place. They're off by, I think it's like 8 or 9 degrees. So they're not entirely in the same location. If you follow your compass all the way north, you will not wind up at the North Pole. You will wind up at the S magnetic pole, which is like over 100 miles away from the North geographic pole. You will not be standing at Santa's house. I'm sorry. Your compass won't lead you there. I mean, you could, use some navigational tools and work that out, but the magnetic pole, you're saying? It's not that far down. It's not that far down. Yeah, you might be thinking of what we're about to talk about in a minute. So, next thing about geomagnetism is during the 1950s, one of the things we decided that we needed to do for military purposes was map the seafloor. 1940s, what technology had just come around that we figured, oh, we need to know what the bottom of the seafloor looks like? Sonar, and more importantly, submarines. So prior to the 40s, submarines weren't a thing. We didn't have to worry about what was under the surface of the ocean. We just went on top of it, called it good. Now we need to know, where can submarines hide? What are they going to hit if they go down there? What's it going to look like? So a large, what's the word I want? Undertaking was made to map the seafloor. One of the things that they discovered when mapping the seafloor was that the seafloor was magnetic. And if you took the mid-ocean ridge, that thing in the middle of the ocean where lava pours out of it, and you moved out from mid-ocean ridge, we found bands of magnetic flooring. So if this is our mid-ocean ridge, this all had a section pointing this way, and it was, as you move out from the mid-ocean ridge, they have identical bands on either side. So we have a section that points towards our S pole, then a section that points towards our N pole, then a section that points towards our S pole. And as we move over that with a compass, the compass flips back and forth and back and forth, showing that as material comes out of the mid-ocean ridge and cools, it becomes a permanent magnet. It's extremely hot, and it's in the presence of Earth's magnetic field. So it becomes a permanent magnet, locking in those field lines at that time. But that also means that over time, Earth's magnetic field flips, and it goes back and forth and back and forth once every, I believe it's like 10 million years. The last flip was about 20 million years ago. So we are definitely overdue for a magnetic flip. What causes magnetic flipping? This is one of those great ones where not only do I get to say, I don't know, but I get to say, nobody knows. Something changes in Earth's convection. Yeah, our magnetic pole will not just flip, but it will migrate over time. So this S pole, and some studies have recently been shown that they're actually currently beginning to migrate. What influence will that actually have? Well, we're going to have a different location for northern and southern lights. They're going to like be over the middle of the planet for a while. Animals that use the magnetic fields for migrating are going to be a little bit off and have to adjust over generations to follow the new magnetic paths. And this is the one that we really don't know how it works, is we've never had electrical grids before. And as you'll learn more in the next few weeks, moving magnets around an electrical line can cause changes, and we don't really know to what extent. Probably nothing extreme because this isn't going to be a fast change. So not an extreme amount of force could be exerted. Is it going to be measurable or noticeable? We don't know. Yeah. Yeah, our compasses are going to be backwards. Yeah. So Earth's magnetic poles, millions of years. Poles are flipping. Flipping is a verb, not an adjective or adverb. All right. Now, questions about geomagnetism, since we made it really weird. Yeah, probably not. I mean, I'm not going to anticipate any asteroid that's not just going to come wipe us out. Probably not. I would be highly surprised.